that the problem is that the issue is too complex to do it in regular computers as we have them today. That's why we can simulate short parts, up to 50 residues long. Much longer than that is impossible at this point. I showed you about these 3 zones. Alignment is very simple in the daylight zone, and I showed you that in this daylight zone we can also do comparative modeling that allows us to tap into the resource of known 3-dimensional structure. One protein structure costs about 100K, about 120,000 structures available. Here's the synchrotron from CERN, 15 kilometers or 30 kilometers is the diameter here. It gives you an idea about the size of this operation. We use for comparative modeling, we use the fact that similar sequences produce similar structures, and essentially the good news is we can sort of leverage the structures in the PDB and do a lot through comparative modeling. So here we sort of add value to the known structure in terms of if I had to do an experimental structure for those, this would be in the ballpark of many $1 trillion. It's a tremendous value that simply is produced by sort of leveraging through comparative modeling. It's an immense value. Now the bad news is we can only do that for sort of every other protein and not for every other residue. For fewer than every other residue. And essentially in order to predict 3D structure, comparative modeling is the answer, but that in terms of numbers really is the only thing that works. And numbers in terms of large scale. And for the remainder of the lecture we're going to talk about reduced predictions, such as reduced to a string of secondary structure, reduced to helices, beta strands. And that gets into the point of are there any questions on this topic of comparative modeling, on topics we have discussed so far? So I had this slide in which I said that when you have bless you, Cécile Pain-Pipe from René Magritte, so this image or the model, that is not the truth. So if you have a model, how could you assess whether the model is right? So you use one of the modeling software packages, Modeler, Swiss Model, and you create a 3-dimensional structure, a model for your protein, your query protein, and you look at it. How do you find out? I said to you, you should find out where it's wrong, where it's more right. How would you actually do that? How could you see whether it's right at all? What could you look at?
Try to run the model with something that you already know the answer. Right.
In that particular case, what you would create is you would essentially, for yourself, reassess modeling suite or modeler, or so you essentially use any tool. In this particular case, it would be a 3D modeling tool, and you would try to reassess that tool with what you are familiar with. For some proteins, typically, if developers do a good job, they have used many thousand proteins, and you would sort of use 1 or 2 or something, right? So you would essentially do a worse job at assessing than an honest developer. And you would do a better job at assessing than a not so honest developer, right? And many people do that. That is in fact one way. So then you see that the method sometimes gets it right and sometimes wrong. The question is for your protein, for your model. Well, that would then tell you sometimes it's right and sometimes it's wrong, right? And it would give you possibly a number to specify what sometimes means. But now what? You are sitting in front of your model. How do you learn from that? Again, so you learn from it in the sense that you know it tends to be wrong maybe in certain places, on average, but is that true for my model? What could you do? And I believe I should clearly state what Mariana said is what many people do. So I'm not saying this is the wrong approach, right? By all means, always do that. But be careful So if you have honest developers, they might have done a better job at it, and you should also look at that. But this is still not all you can do, or all he can do. It's still not really completely giving you the answer for the model that is in front of you, for the solution that you have. What else could you do? Any idea? Yeah?
Test with another tool and compare it to objects.
So that's a great idea. This does not imply that that was not a great idea. Is another great idea. And somebody had the great idea of taking my black markers again. So let's just do that in terms of secondary structure prediction. So say method 1, so that is the one that you actually look at, method 2, and so method 1 has something like this one here. So now, this is supposed to be the prediction here. So the H, sorry for my writing, that's why I use slides. The H is essentially helix, so this particular resonance is predicted in a helix. The underscore means it's in a state other, so it's neither helix nor extended, or nor beta strand. And I compare method 1, which is the one that I sort of meant in this comparative modeling. You get a comparative modeling. How do you assess whether it's right or wrong? In this particular case, it's a secondary structure prediction. And 2 is the one that Tatjana suggested try another method. Now what?
Oh, we only know that the 2 methods say something different, but not which one is the...
That's the problem, right? So now you do say, you may now say, okay, it builds my trust that I have something that is helical and that is sort of something other here, because that is a consensus. So both methods agree on something, and I believe this is more likely to be true. So that's already something that you could come. I'm not entirely. I'll get back to whether that is right or wrong in a moment. But this is one way in which you can use that. Another way of using it, but another issue that remains. I'm going to get there now. Natalie says, for this particular case here, where we have a conflicting prediction for these 4 here, for which we have conflicting predictions, we do not know, is method 1 right? Is method 2 right? Are both wrong? So I have a second opinion, so to speak, and I'm not entirely sure what to make out of it, because for my individual place, for my first prediction, I still don't know whether that one is right or wrong there. True. Now, in particular, you immediately see that, okay, let's try something else. Say we had 2 random predictions, random 1 and random 2, and say they would agree both on these other predictions or loop predictions. Would that make it a meaningful prediction? Because they're random, by definition, they're meaningless. And if 2 random predictions agree, and if I have 3 states and a long protein, that will happen. So if I have random predictions for 3 states, some will overlap. And only because you observe that between 2 different results here by default, by construction, they are random, is totally not meaningful, right? By construction of random, there is no meaningful correlation between 2 random predictions. And now the question remains, even here, if I have method 1 and 2 and they agree, it still could be the random overlap. So in order to sort of compile how meaningful that is, I would have to somehow see the random background. I'm saying this to just say it may be a very good idea to look at a second opinion or a second output, but it is not so clear how to benefit from it. So by all means do it, but be careful in using it. That's what I'm trying to say here. So first of all, do not jump on agreement and say where they agree, I trust more. That makes some sense, but it's not completely right and not completely necessarily right. Secondly, if method 2 would be way worse than method 1, and again, in what Mariana proposed, we could imagine that we are sort of looking up in some large data set that we know of, we test both methods and we see that method 1 is absolutely better than method 2. And then from that you would conclude that by all means where they disagree, you're not really looking at agreement and disagreement, but if this is much worse than that, you would still tend to believe this one more, and the question then would become, what do you learn from the second one, right? If you essentially say wherever they disagree, I tend to believe more in one because on average method 1 is much better, then it gets tricky to see what did I then learn from 2, and it's actually complicated. It's not that easy. You will do that. All I believe I'm trying to induce in you here is be careful. Another way, so I thought about this comparative modeling prediction, because one answer that many people would give is run some energy optimization over it. So look at, I have a 3D model, does it make sense in terms of energy? And that is tricky because this is built into all the modeling pipelines already. And your energy minimization may be a simplistic version of it. If a simple way of improving the model would improve the model, the pipeline would have taken care of that. So simple ways are not the ways. The only way in which you can do it is you have some additional knowledge where the active site is. You have some additional knowledge where you suspect the active site is. You know something about its binding. And then you look at the model and see whether that is reflected in the model. This is true here too. So you see that there is something that is predicted as a long helix, and that is something that may be DNA binding. That makes sense. Maybe if you believe that here is a DNA binding site, or you have some additional data, or independent data that the DNA binding site is here, maybe you would believe method 1 much more than method 2 on this particular case. So the best way to make sense of a model is bring in new data, bring in your new expertise. And this is not necessarily the expertise of using some data for which you know, but additional things that are valid for your particular prediction. This is the most relevant way of doing it. Okay, back again to secondary structure prediction. Again, secondary structure prediction is a string. Most residues, so the entire pi is all the residues in 111 million sequences that we have in UniProt, and about that fraction I cannot predict 3D structure for. About that fraction I can predict 3D structure, and about that fraction I have experimental 3D structure. So the bad news is for most of the residues we don't have any information about 3D structure, so we have to go back to simplified predictions such as 1D, such as secondary structure. The simplest solution for secondary structure prediction is you look at known structures and, for instance, find the longest consecutive run of a helix. Okay? So longest consecutive run of a beta strand. And you essentially take all the known helices, all the known strands, and you have a sequence for them, bless you, and then you essentially look up, does my sequence, for which I want to predict secondary structure, have this helix that I know? Okay? This is one way in which you could do it. Now this is not going to work very, very well, because most of the helices will not be in your protein. Most parts of your protein may not be matched in any protein out there in terms of identical sequence match, right? So this is in fact a simple idea, but it's not going to get you very far. The first actual prediction method was even much simpler, and it goes back to something that Pauling, in the way he defined helices and beta strands, Szent-Györgyi in fact published a paper in Science in which he argued that proline breaks helices. And that, in fact, is the first prediction of secondary structure. If a proline breaks a helix, you know exactly that there is a helix, right? Interesting enough, publication date is 57 here. The first structure was published 58, the second one 60. So this was a secondary structure prediction before a structure was seen. Before these two structures came out here. And this is Albert Szent-Györgyi, who got a Nobel Prize for something else, not for the secondary structure prediction, biological combustion process related to vitamin C. And vitamin C, in fact, is the molecule for which also, in which Linus Pauling worked a lot, who wrote the papers that got into this idea. So again, ultimately what it is you look at some particular feature of one particular amino acid, proline, and you conclude something about secondary structure. And now if you sort of expand on that, the simplest method then would look at features or propensities of individual amino acids for certain secondary structure states. So the way you would do that, you start with one particular protein. Here you have the sequence, you have the secondary structure, where the blank is the state other or loop. These two dots imply that this may be a beta strand, a longer beta strand. And then you simply count. You see the first Q, you see this is in the state other, so you have in this particular case only two states because there's no helix in this molecule. So we have Q, you put a count for the state L. You do the same for every letter, so the sum here is 1, 2, 3, 4, 5, 6, 7, 8, 9. 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. 2, 8. So this sum here is 8 because you have 8 blues here, 8 extended, and then whatever number of dots or not blank spaces you have, L's you have, is down here. So you do this, you build up this table for all proteins in your data set, and you have a probability table, right? You do that for 3 states, of course, usually, and you get something that is known as the first generation method. There's one type of method called Chow-Fasman and GOR, named after the people who did it. Here's the paper that got the GOR is Garnier, Osgothorpe, and Robson. Barry Robson was the one who sort of did the math. Underneath, you see the first idea is here in 71. And Jean Garnier is the one who sort of got the biology in it. The Osgothorpe got the structural biology into the story somehow. And again, ultimately, this is exactly what it does. It's a simple probability for a central residue. A simple probability table. Where do we get the secondary structure from? Well, we get it from DSSP, and ultimately, Chris Sander here and Wolfgang Kapsch, they came up with DSSP to assign secondary structure from 3D structures because they wanted to develop a secondary structure prediction method and they wanted to assess those prediction methods. That's why they developed DSSP at the first place. Again, I briefly mentioned that Chris Sander, this HI index is much higher now, immensely visible, person computational biology. Okay, so how good are these? So how would I measure? How would you measure the performance in secondary structure prediction? So this is the observed secondary structure prediction. This is the predicted. How do you compute performance? How do you compute accuracy? You don't. You come, shoot. Yes, so by the way, if you were more into the computer side of it, you would look at it in edit distance. So you would look at what would it take in terms of edit distance to turn one string into the other. This is not quite the same. So count where they agree essentially means what is known as the Q3. And my interpretation of the 3 is, this is not the reason why it's called Q3, but this is the way it's sort of now, I believe, generically understood in the field, Q3, because it's a 3-state per residue accuracy. So you have the 3 states, HEL, or other. I'm going to call it L because most slides have L. So HEL. And for those 3 states, you simply ask, what's the fraction of correctly predicted in those 3 states? That's what you count. The match of the 2 states. That's exactly the answer to that match. Now, the Go and Chow-Fasman had published levels of accuracy of 63%. When the first DSSP looked at it, 55 were counted. When I looked at it many years later, the performance had dropped slightly because there was a larger data set, much larger data set, and then performance was around about 50%. Okay, 50%. Is that high or low? Well, it's not outstandingly high. It's not 100. This is very clear. What is 50%? I mean, how do you react to 50%?
In comparison, how good the other algorithms are.
That's fair enough, Luis. So you could compare two methods and then you would see whether one is better than the other. In this particular case, in the early days, Chow, Fassmann, and Gore were performing at a similar level of performance, both sort of 50. Now, my question back to you, is 50 high? Good, bad?
Well, it depends, like on the random classifiers, that would be, I think, 30%, like a 1/3.
Well, 30% is more 33, right? But so it is better than random. That's a very important statement from Pia. So you always have to look at the background. Since the three states are not equally distributed, the random number actually becomes slightly higher. Okay, if you have equal distributions, 100 by 3 is 33.3. If one state is overrepresented, the number gets higher. The random, if you do it here, is 35. But you may remember that if you just look at what's the fraction of helix, this is round about 30%. E is around about 20%, it's a little bit higher and lower here. And L is around about 50%. It's not quite right, but round about these numbers. So for my entire data set, about half of it is loop. So can you think about a simple prediction method that would get a good Q3 of 50%? That would be as good as that, and it's totally stupid?
You could always predict loops.
Exactly. And actually it's not that easy to, if you look at Q3, you can absolutely not see whether that is what your method does, right? Yeah?
And maybe you should look at the accuracy for the different steps.
So then, Tatjana's right. So in this particular case, the beauty is you would now pick up the absolutely stupid aspects of your method, or would pick up a very stupid method, because this would have 0, 0. For helix and strand it would have 0, and for loop it would be 100% right. So you would see that there's something going on that is weird. The downside to this proposal is you would have now to always quote 3 numbers. So if you compare two methods, it's already 6. So you see that the complexity grows immediately. Now you could do some sort of mathematical operation. You multiply them with each other or something. The problem with that multiplication, the advantage is you can turn so you do a cubic root of the percentage correctly predicted helix times percentage correctly predicted beta strand times percentage correctly predicted L. For the dumb method, it would be 0. For the random method, it would be 33 or 35% of 0.35 or something like that. So you would clearly see that the random is better than the dumb random in this particular case. But you would unfortunately lose the intuitiveness of the score. So by multiplying these 3 numbers, you cannot quite interpret what that means. So if it is 0.5, that could be created by being very good at helix or very good at loop and not too good at the others, or it could be equal. It is not easy to see. Anyway, so there's something that we learned from all of this already. We need to look at several scores, and 50 is better than random, but not that much better than random, right? So I call them the first generation method. And the first generation method simply, again, looks at the propensity of an individual residue. When you look at the way a beta strand is forming, you see that there are neighboring residues that contact each other. So, not each other, I'm sorry, in a beta strand. So the contacting point here is between 2 residues, J and J minus 1, and I minus 1. So I plus 2, sorry. Every second residue is binding the beta strand. Let's turn it around. Let's begin here. So this is I, this is J, this is J plus 2, I plus 2, J plus 4, I plus 4, blah, 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 blah. But they always bonding, right? You see that the next residue is bonding 2 over next, I plus 2. So there is some pattern in the neighborhood. How could I use that? So I'm not talking about this binds that one. Using that is a different story. I'm only talking about the fact that there is something happening in my neighborhood. My other next residue is also going to have a hydrogen bond. When I want to be in a beta strand, right? How could I possibly put that into my system? In a very simple way without being explicit. I know this sort of information is important. I don't know how to label it. So I cannot say amino acid type this is a hydrogen bond former. This would be a different story. Just the fact that I have importance coming from next in my sequence. How could I put this into a prediction method? How could I refine a method from what I'm doing so far, which is an individual probability for each amino acid? How can I improve over that? I'm sorry that I drank. I need to be lubricated. Yeah?
Take a K-mer for
K-mer or something even simpler. Look at some segment. And by the way, segment, the original idea of segment here comes from Kapsch-Zander again. And that was the idea. So they thought about a K-mer. And because they thought about a K-mer, they needed a large data set. For k equals 3, you already have 8,000 possibilities. For K-mer optimization, that means you need a large database. In those days, in fact, for their first database, they had something in that ballpark, just around about 8,000, but not much more. Now, the simpler approach here, simpler in terms of numbers of samples that you need, is not the segment-based approach, but is what is put into Gore 3. And again, so the math comes from Barry Robson. It's not that easy, the math. But essentially, all it does, it assumes that you have a particular amino acid here at this position, and then you compute the probability of this one breaking a helix, this proton breaking a helix, conditioned upon those other 3 being particular amino acids. And in order to compute the probability here, the way you can think about this is you do the same table as before, but now you have, instead of 1 amino acid, you have 7. This means that now you sort of shift this window of 7 consecutive residues through your protein. A protein of 100 residues creates 100 of these windows. That means that every window counts for my probability table, not like in a K-mer. In a K-mer, I have to sample 20 by the 7. So I have to have so many samples that 20 by the 7 samples I have. Here, I don't do that. I simply count the number of occurrence of whatever is next in all my samples. This is simpler. So this gives a conditional probability. It does not give all the space of K-mers, right? And that is why this is much simpler than the segment approach that I said before, or the K-mer approach that you may have meant. It's just a simple conditional probability. Again, conceptually it's simple. In terms of filling the probabilities here, it's simple. Mathematically, it's not that simple to write it. The equations get tricky because conditional probability is just not easy to do, or it's not that intuitive to do for people. Okay, so the problems with the first generation methods were the first one was really, it's not 100% performance. Okay, the reason people said is there is a maximum. The maximum is 65%, and this maximum is reached because some secondary structures form more locally, like helices. Some secondary structures formed less locally, like beta strands. In fact, there's the second problem here, that beta strands are predicted at levels very close to random, because beta strand formation is not local. And in my window of 7, or even of 13, I do not see the binding partner of the beta strand. I do see the binding partner of a helix, but not of a beta strand. So the third problem was that segments were predicted very short. So let me illustrate that problem. That's the observation here, the secondary structure. Up here is the sequence. And here is a typical secondary structure prediction. Now in the typical signal structure prediction, since all those things are relatively short, that leads to a situation where you don't know here, is this a long helix? So do you actually have to switch these EE to a helix, or is it really a short helix and a short beta strand, or is the helix wrong? Is it a long beta strand? And a similar problem here. So if the segments are too short, you're constantly in front of the decision. So maybe here you're completely clear. This should be a long helix. Again, if you look up what the reality is, you see this is wrong. But one problem really of short predictions is you cannot guess right what should you as an expert correct it to. Now I mentioned here in the first slide, they said that 65% is the max of a prediction method because 35, so 100 minus 65, is what is non-local. How did that statement come about, do you believe? What made people claim that?
What, sorry?
So the experts claimed, and I have to go back into slides, I have to really change this. Expert claimed here that the 100% is not reachable because the maximum you can reach is 65% because everything else is determined by long-range interactions which I cannot pack into my window. So 35% is not determined by local interactions, so maximally I can get 65. What was this statement based upon, do you believe? You do not know, so it's all guess game, so guess. In fact, it's very healthy that you do not know, because it means you were not around 30 years ago. You're young, by definition. And being young is healthy. Anyway, any idea? Throw some wild explanations at me. How could you measure it? How could people come up with that? Insert here a machine learning device. The idea of neural networks. So neural networks essentially are devices made up of neurons or units. In blue, here the input to the device. So this is a layered device that has an input and an output. The unit here has a value, 1. This one has the value 1, 2. There's a connection between the units, the J. And the way the computation works is you multiply the value you have on this connection here with the value that is this unit. So 1 times 1. That comes here. Now this unit here integrates, so sums up. Meaning it sums this times that, this plus that times that. And then ultimately what this implies is you have a vector of connections and a vector of input. You project two vectors onto each other. That is what you do geometrically. This is a vector projection. And then comes a nonlinear decision function, a trigger function. Shown here is the hyperbolic tangents, typically a sigmoid function, very similar, which works the following way. If what comes up, the sum here, is very highly negative, you switch it to 0. If the sum is very highly positive, you switch it to 1. And something in between that can be differentiated. A simple function. You could also have some other function in here. So this value is what comes in, it's the sum here, and that value here is what goes out. So the output from this unit essentially is between 0 and 1. That's the nonlinear step in between, and that's like deciding whether or not this vector product is longer or shorter than something. This is the way you can imagine it. So the classification, this is an open circle here, the classification that you can do in order to train this open circle. So the mistake you do, so there's one, this is the unit 0, 1, and this is the unit 1, 0. The mistake that your method does is what the network gets out minus what you want to have it as output. So say this one you want to project to 1 and this one you want to project to 0. Then you simply see what you get so far. You subtract and you square to make it sign independent, and then you get the error. And in order to train, you have the connections. That's the only thing in the device that you can change. And you have the error. So there's some landscape of error versus connections. And what you will try to do is, during training, you will change the connection such that it go downhill. Very simple, right? Change to go downhill means that for one pattern here, for the open circle, you want to maybe map it to a 1, and for the other one you want to map it to 0. That means you have to sort of change the connections. So in this particular example, if you look through it, you have to make this connection here higher. So you build up higher, higher, higher. The other one you have to make lower, and this way you sort of differentiate them. And this is training a network, and ultimately what you do by training, you introduce a line into your points. In the case of the open versus dark circle here, 4 different lines do the trick. They all do it. For my training set, they do it equally well. So these are essentially 4 different neural networks that find 4 different solutions that in terms of training are 100% right. Okay? How can you find a line that separates these points? Yeah, you have seen that before, no? So somebody who hasn't seen that before. And they don't have... How can you make a line? Well, this is one answer. Of course, it's not a straight line, and the language of the neural network that I described so far can only do straight lines. So if you do it with straight lines, you need 2. And 2 lines in the language of a neural network essentially introduce a new layer. It's called hidden layer, often referred to as a hidden layer simply because this is input, this is output, and this is nothing. I mean, it's hidden somehow. It's just doing some mathematical operation in between, right? It creates one way of thinking about it. It sort of projects the problem into a higher dimensional space. And this higher dimension, I'm very careful with animations, but sometimes I fall victim of it. So the number of dimensions, one way of thinking about it, are given by the number of hidden units you put in. So the more you blow this the more hidden units you put, the higher dimensionality, the higher dimension you sort of project this into. In terms of math, it's the same as before. You take this value times that. This is the input here times the connection. This is here. You sum over the 2 that come in here, and that's the input here. Then you put the trigger function. That's the output from here, and then you do the same thing. You take the input here. This is this. Multiply with the connection. You sum over these 2, and then you do the function again. Same as before. So mathematically totally trivial, there's nothing new, and also the way you train the device just essentially still is a vector multiplication. There's nonlinear trigger, everything as I said before. The output error is here, the training into reducing error space is just what I showed you before. So you take the error, you differentiate with respect to the connections, and this means you go downhill, that's why it's a minus. Epsilon means you make a little jump. You don't go too far, so you don't jump too far. Let's not talk about why. You make little jumps in the direction downhill. In the direction downhill, in this particular example, you would at some point get trapped, so you allow an uphill move. That's referred to as a momentum term that essentially allows you to go uphill by adding something that is related to what you did in the time step before. When you do this, sometimes something like that happens. What is that? So what I show here is training time. What I show here is performance. Performance in terms of 100% right, 50% right, 0% right. So what may I show?
Overfitting?
Over training, over fitting, exactly. And so this is the kind of typical thing that is called, that is true only for toy problems. So things never look like that in reality. They look like that in lectures, and they look like that in toy problems. They look like that on the web, but not in reality. They look like that when we want to explain something. When you apply machine learning, the world is never as simple. But okay, what are these curves? The blue and the green.
Green one's the training curve, the training time, and blue one the
Yes, and so this goes back to the cross-validation idea. So in cross-validation, the pi is all the data that you have. And all the data you have to split into different sets. In fact, you have to have a threefold split. Tatjana just said a twofold split. I will explain in a minute why threefold. But ultimately, at least you have to have some fraction of the data for training and some fraction of the data you hold out. You hide under the table. You pretend to simulate what you will see tomorrow. So this left out data here, for instance, the part that is in blue, the test set, is the one that you pretend not to know. And with that you test how well your system has actually learned generic rules. Okay? Because you hope that machine learning extracts some principles from your data. How well does it do for extracting these principles? Well, ultimately, you will see tomorrow how well it does, but tomorrow's data you don't have today, and the blue one here is the simulation of tomorrow's data. Okay? Now, here, for secondary structure prediction, is one typical example in practice here from secondary structure prediction, number of training cycles. So the further that goes, the more you actually train. And this is the classification performance. And this is, in fact, the training set, and this is the testing set. Okay? You see that this idea of toy problem, there is some sort of optimum. But it is by no means as clear where the overtraining starts. In fact, if I asked you where's overtraining starting, what would you say? So maybe you would say that the highest, numerically, the highest point that you reach is this one. So overtraining is here. And this is most likely if you sort of, in most cases, you will define numerically highest value as the top point, and this will exactly be the point. Now, when you, another way of looking at it, just look at this point here, what you see is that a lot happened to the green set, very little to the blue set. So maybe actually at this point here, from here to here, there was much more that went into optimizing the training set than optimizing the test set. So maybe already here is a point beyond which most of what the system does is learning something by heart. And this is what overtraining means, right? Overtraining means that you fit a response that is relevant only for the green data set, the training set. So you find answers that are right only for training, that are not right for the data from tomorrow. And if you want to avoid that, maybe actually more left of what numerically is the highest value would be the best pick. And you see in this particular example, although it's relatively simple still, it becomes already tricky to choose. The tricky to choose part is in fact exactly what you need this cross-training data set for. Here I call it cross-training. You need that data set to decide on other, what is often called hyperparameters. So the hyperparameter could be, when do you stop training? So what is the network that you call your final solution? That essentially means you have to stop at some point here. You don't, I mean, this is just for instructional purposes to show this curve, but in principle, the network that you take for prediction, you should have cut somewhere. And the cut would have to be decided on the light green here. So that's why you need a third data set. Let's get back to the issue of secondary structure prediction. So we have these three problems. If we implement such a solution as the neural network, this is one way of doing that. So now my window here is 13 residues long. In brackets you see the secondary structure of this particular residue. What the window learns to do is predict the secondary structure of the central residue. Here's the P. And note this P is happens to be in a beta strand. Now, what I cut out here is these blobs. You see, there are 13, so there are 13 amino acids, and there are 13 blobs. Each one of these blobs here essentially is a vector with 20 units, or with the 20 amino acids, where one is on, the P, the others are 0. Okay? Now, if I take this, and on the whiteboard, I'm just going to, instead of a window of 13, I take a window of 3. So I have a residue 1, 2, 3, 4, 5 in my protein. Okay? So my first window of 3 would predict the secondary structure for residue number 2. My second, then I slide the window by 1. My second would predict the secondary structure for 3, and I slide by 1 for 4. So this is 2, 3, 4, right? What's the problem with that? With that solution? Somebody who has not taken last year's course. Can somebody give the answer who doesn't know the answer? Yes, exactly. So it's a tricky... So anything you guess is fine, is what that means. I want somebody to respond to that who doesn't know. So that means that anything you say is as good as you can guess. So when I slide this window through, again this is 13 in my case, I'm just too lazy to show 13 here, so I show 3. If I do this for my 5 residues here, I would get, that's what the next one would be, 5 here. No, actually no. That's it. So if I had a protein, a peptide, it's not really a protein, a peptide of 5, then I would have 3 windows. Is that clear what is wrong? Yeah?
Yeah, you can't predict anything at the start and the end of the step.
Exactly. So residue number 1 is not predicted at all, right? For my window of 3, it's only 1 that I skip. For this one here, it's 6. Yeah. It's 6 that I miss, right? Now you may argue, okay, missing 6 in the beginning and 6 in the end, 12 residues for a protein of 100 residues is at least 10%. And if your window gets larger, you miss more. How could you get around that? And the idea is you introduce a new amino acid, a pseudo amino acid, a spacer unit. And this is in fact why you see here is not 20 but 21, where this is the spacer. The spacer is on. So this way now the first window is this one here, with this one in the middle. The first window has 1 spacer unit. And in the case of 13, the first one simply has 6 spacer units. And at the other end, when I slide through, I could have a 22nd amino acid, or another spacer for end and beginning. When I tried that first, it didn't help. So ever since I've used only 20, and everybody has copied that. So the whole world uses 21. Anyway, so other than that, the idea of the sliding window is clear. For everybody in the room? So I simply slide this window through. Okay, now, how could you change that? So in my particular solution here, you could have, I have 13 consecutive residues. You could take 15, you could take 11. This is not what I'm asking. True. So I could change the window size, right? Let's assume that because of some reason or other, and it's nonsense, I'm just for now, let's just keep the 13 fixed. Because I happen to like 13, okay? Stay with me. And what else could I change? So this will create 13 times 21 input units. How could I do the same thing with fewer input units? So sticking to 13, to windows of 13. How could you reduce the number of input units? Yeah?
Maybe group amino acids with the same features.
Yes, so this is in fact already way beyond the simplest solution. The simplest solution is you put a number for each amino acid, right? So you take a real case number. So alanine is from 0.05, from 0 to 0.05. And cysteine, the next residue in the alphabet, is from 0.06 to, and so forth and so on, right? You simply have the 20 amino acids, each gets a number, and essentially you would have 13 input units. Well, to 21, you need a spacer still. But it's still 13 input units, right? But you can essentially code each amino acid as a number. That would be the dumbest thing. The clever thing would be what Tatjana says, you look at some biophysical features. For instance, you could say, well, amino acids, they have a size, they have a charge, they have a polarity, they have a hydrophobicity, and then for each of the 20 amino acids, I have a vector of 4 components, with a spacer of 5 components, and then I simply put the ones and zeros for each amino acid according to which of these features they fit to, and then I would have 13 times 5 instead of 13 times 21, right? That's one way of doing it. What else could you do? Well, you could sort of optimize the coding according to how well you perform. You could try a bunch of different coding versions of coding, and you could see which one performs best for my particular task. Now, it turns out that what is often referred to as sparse coding, the one that uses 19 or 20 zeros and 1 1 for each amino acid or each residue, performs the best. But ultimately we tried to put the machine learning device in because we wanted to have a method that performs better in secondary structure prediction. Okay, this is how it performs. It gets a Q3. You want me to switch it off?
No, okay.
It gets a Q3 of 62%. Which in fact is not at all better than any of the other methods out there. And at some point, so when I first saw this, I was very disappointed because I thought that this is such a cool tool. When I first applied that 28 years ago, it's such a cool tool and should actually help. There's so much intelligence in doing this, so somehow this intelligence should work, but it didn't work at all. Then I looked at this. So I looked essentially at the performance over time, training time. So in this direction, I train more and more and more and more. In this direction here, I show the performance, the accuracy. I show it separately for the 3 states, helix in red, strand in blue, and the other or loop state in green. What do you observe?
Performance for strand increases, but for helix decreases.
So blue goes up, helix goes down, and this is sort of staying constant. That's one observation, right? Why could that be the case? So if you apply machine learning and you saw anything like that, let's not think about secondary structure. Think about what you have 3 different states that you try to train. One is difficult to learn. Why could that be the case? What would you suspect? Yes?
It's just not that often observed.
Number. So one issue is it could be very tough to predict strands. And one issue is it could be we have few beta strands. Actually, let's look at this the number of correctly predicted residues in a slightly different way. So 62% of the residues are correctly predicted in either of the 3 states, helix, strand, other. Now I ask, what of the fraction of this 62% that are correctly predicted, what of that fraction is helix in red, what of that fraction is beta strand in blue, and other? Okay, this is the fraction. So the whole pie is my 62% correctly predicted. And of those, the largest fraction here is white, so it's the other state. If I now show you those 3 states in the data set that I use for training, that's that. What jumps at you?
It's the same distribution, so
Very, very similar. So essentially, you learn the distribution that is in the database. You may now call that overfitting, you may call whatever you wanted, but this, it jumps at your eye that these 2 things are very similar. If you had a database like this, how could you create a database like this? Well, one way of doing it is, so in the error reduction, by changing the connections in the neural network, you present one sample at a time and then you go a little bit of epsilon downhill. Now instead of this, I'm going to sum here over 3 residues. So at every single time step, I'm going to pick one that is a beta strand, one that is an alpha helix, one is the other. Which is, I'm going to oversample beta strand. Because I'm going to sample them all equally, that means that I oversample the underrepresented classes, right? I present them exactly in this ratio, exactly equally often. Okay? Let's see what I get. This is the unbalanced story that I just showed you. So this is as they are in the database, and this is if I present them equally. So the red part behind you don't see because they're exactly on the blue. So this is the network. Okay? So what we learn here is you can, if you understand your problem, you can do something better. The something that you do better on is now beta strand is predicted much better than random. In fact, it's predicted not only better than random, it's predicted equally good as other, or loop, and helix. And now that gets into an interesting explanation. We said beta strand is predicted less accurately because the formation of beta strand is less local. Makes a lot of sense. But I just showed you the prediction device. I mean, I showed you in the slides before, I showed you a prediction device that just takes beta strands more often and gets the same performance for beta strand. Conclusion? Not all explanations that sound good are right. So this explanation about beta strand, the world is still, you find still publications where people argue that beta strands cannot predict it equally well because of less local interaction. Because it's intuitive, it's right, but it's not the reason. Because you can create an equal prediction. And creating an equal prediction without using any sort of more global feature means that the information that is contained in the local window is exactly the same. Okay? Which is surprising. In fact, that is the most surprising finding here. And this is an example where from the machine learning you actually learn something about biophysics. We can do this one here. Now, I want to attack this issue here, the issue about short segments. One way of seeing that segments are predicted short is what I showed you gets an average beta strand of length 3, an average helix of length 4, while the average beta strand in the database is sort of 5, and the average helix is 10. So this is observed, it's much, much longer than this. The reason why that happens is because when I do my error minimization, I said I pick a sample, or in the balance method 3 samples at the same time, but I pick these samples randomly. Randomly means that at time point t and t plus 1, I typically take a sample from a different protein. I cannot slide through my one protein because then I would sort of bias the training by particular proteins. In fact, that goes very wrong. In the practical, let's not go into why and what. It tends to fail. So in time point t, I take the first residue, at time point t plus 1, I take the next residue, and so forth and so on. So I go residue by residue through the protein, then through the next protein, through the next. That is the wrong way of doing it. The right way of doing the training is you randomly pick You have 10,000 proteins, you put them all into a database, and then you randomly pick out of it. Okay, and then you present them this way. If you do that, you completely lose that helices I and residue I plus 1 are correlated. That the helix has to have a minimal length. You lose that because in the next training step, you have some other protein. You have some other segment. You never see helices. How could you change that?